Hello class, in this lecture we're going to talk about supervised learning. So if we look at the larger picture of the course, we are still working through understanding the difference between supervised and unsupervised techniques and the math behind them, and getting to the point where we can execute supervised and unsupervised machine learning techniques. In the next module we'll talk about evaluating various types of machine learning techniques and how we do that performance evaluation. And over the course of the semester you should be, through your module assignments and your medium posts, explaining results that come out of your evaluations and assessments. And then finally, we'll end about critical evaluations for the accuracy of these different algorithms. Looking specifically at supervised learning, though, in this first part of the lecture on supervised learning, we're going to talk about differentiating between classification and regression specific to supervised learning, how voting is used for k-nearest neighbors classification, different kinds of classification from the binary case to the multi-class case, and then the multi-label case and how that's different from multi-class. And then we'll end with a brief discussion about overfitting and its impact on how models generalize. First, talking about classification and regression, recall from several lectures ago when we talked about defining machine learning, we said it's an overloaded term and generally the study of algorithms that quote-unquote learn from data, where what we might learn might be structure, or we might learn to generalize from examples of a task, where we have some input data with some information about that data, and we want to be able to make predictions about new data that's similar to our input data. In this case, there are two primary kinds of machine learning problems: unsupervised learning and supervised learning. There's a third type that people talk about called reinforcement learning. We won't talk about that in this class. Primarily, we're going to focus on these two. And in particular, we're going to focus on supervised learning, where from the unsupervised learning perspective, we were interested in structure. Here, we're much more interested in generalization. So how do we know if we're talking about supervised versus unsupervised? In the unsupervised case, you're focused on structure, but you don't have examples of what that structure looks like. You don't know what your clusters look like before you run your clustering algorithm. In contrast, for supervision, we do know something about the relationships we want to predict. We have good examples about these known relationships between our data and the outcomes of the things that we want to predict or generalize or infer about our data. Often we talk about this as having labels. We have labels that we are trying to predict, and we have good examples of what these labels look like. So there are two kinds of supervised learning tasks, and the first is classifying elements based on known kinds of labels, this classification. So we are doing some sort of ordering or type, or not ordering, we're doing some sort of typification or categorization of our data. In contrast, we can also be trying to recover scores or orderings of our data. This is known as regression, where we take our input data and we're trying to predict some value, some numeric value, where we have some idea of ordering here. In the examples we talked about before, if we are looking at the news sources that people share, we can be trying to classify them into a political party, either Democrat or Republican, and that's a classification task. In contrast, we could also be doing regression, where we're trying to score an individual in some linear space based on how conservative or liberal they are, where that number is some actual numeric value. Here in this case, the more negative that number, the more liberal the person, more positive that number, the more conservative this person appears. In both cases, though, we have data about this ideology. We either have party affiliation data, or we have some idea about ideology scores, where we know something about these people are more conservative than these people, and we're trying to recover that information. And there's some gray area or some fuzzy distinctions between unsupervised and supervised learning, and whether we have labels. It's like I said in the previous example for classifying movies into clusters, you can apply some clustering algorithm and then use that clustering as a kind of ground truth that you can then use as your set of labels to try and predict in other ways. Here, though, we're going to talk in the context of supervised learning about some terminology, where if consider you have this collection of data or a data set where you have a bunch of measures about a collection of different kinds of fruit, and you want to classify them into whether they are one of two types of fruit. Is this fruit an apple or a strawberry? Now you imagine that maybe this is what your data looks like. You have an Excel spreadsheet or a pandas data frame, with measures about mass, height, color, and whether something is a particular kind of fruit. So this fruit label. Crucially, having this label, if this label is what we want to predict, that's our outcome, then we are in the squarely supervised learning case. So we can talk about this, about some terminology here. You may hear people talk about data instances or samples or examples of your data. A sample set, a set of examples, these are all the sample pieces of your data, the examples that you get that you're trying to predict. So you might expect to see new or unseen samples that have the same kind of structure as your seen samples. In our matrix on the right, these generally refer to the rows of data in your matrix. So each row here, 192, 180, or the row that starts with 192, row that starts with 180, etc. These are separate samples or examples of your data. Each sample also has a collection of features associated with it. These are attributes or properties of a sample. From a statistics background, maybe you might think of this as independent variables. So you are trying to predict something about fruit label. What kind of fruit is this? The independent variables you may have are mass, width, height, and color score. These are, like I said, the columns of your data matrix, and every sample has generally these values associated with them, though you can have what's called missing data, which is an issue we will save for later. You also have a target value or outcome. This is the thing that we're trying to predict or we're trying to infer for each sample. So given some set of features, what is the thing that we're trying to predict? What's the target value we're trying to predict here? And oftentimes this is talked about in mathematical terms as an X set and Y vector, or an X matrix rather, where X is the set of samples in your data and all of their associated features, and Y is the target vector that contains the labels that you're trying to predict for each one of the rows in your matrix. So here in this matrix on the right, these first four columns and all of their associated rows, that generally is referred to as the X matrix. And here this vector at the end, fruit label, is your Y matrix, where your X matrix, your data matrix, is your set of samples and their associated features, and your Y vector is the collection of target values or outcomes for each one of the elements or rows in your X matrix. And then finally, all of machine learning is about creating these models that map or try and predict the outcome variable y given some data matrix x, this function f of x mapping to y of the features or attributes of your data to some outcomes. So when we talk about classification and regression, with classification specifically, we're talking about your outcome variable coming from a set of distinct and discrete elements. In contrast, for regression, we're predicting scores, where your outcome variable y is generally from the set of real numbers. Now, it can be a set of integers. There's ways to maneuver this, but generally this is the distinction. And with your label set for classification, your labels have no order between them. They're purely categorical. There is not a concept of L1 as somehow less than L2. Now, certainly you can do that. There are ways, like I said, everything here is fuzzy, but in the general case, when we talk about classification, we talk about discrete labels that are independent and have no ordering among them. And for regression, we're talking about recovering some numeric value from the real number scale. And there is also multivariate and multi-value outcome here, but we won't talk about that. So given that context, one thing we haven't really talked about yet is how we do some sort of evaluation. We have some model, this f of x to y. How do we evaluate whether this model is doing a good job or is recovering our target variable well? So I'll talk about this only primarily because it depends vastly on many different factors, and crucially depends on whether your task is a classification task or a regression task. And there are many different metrics for evaluation. I'm going to focus on the two most common ones here because we have a whole module associated with evaluation, but it's important that you have the terminology when we talk about testing and training sets about why we do this to evaluate performance. So first, when we talk about model classification or model evaluation in terms of classification, the most simplistic evaluation is accuracy. Basically, how often were we correct in our label prediction? So if we want to turn this into a formula, we have a couple of terms here. We go through this summation over I, which is all of the rows in our matrix X. So this f of xi generally means the function of our model applied to the sample x sub I, which is the row in your data matrix. And then we evaluate whether the predicted outcome from our function matches the true outcome y sub I for that row. And we would make this notation a little bit more sophisticated here by saying this is an indicator function. It's 1 if these two values are the same, and 0 if they are different. So we sum up the number of times we got the label correct, and then we just divide through by the number of samples that we have, and that gives us the average times we were correct, or the accuracy for a given model. Regression, in contrast, is a different kind of thing, since we don't necessarily evaluate whether two values are identical, because we are trying to evaluate how close two scores are. So the most common metric here is the average, or the mean, of the square of the difference between the true and predicted value. So here we talk about error being the difference between what we predicted, what our function returned, our machine learning function or machine learning model returned as our predicted value, minus the actual value that we know from this data. This is the labeled aspect for the supervision. So it looks pretty similar to our accuracy metric. We talk about this as the mean squared error. Again, we normalize by the number of samples in our training set or data set. And here, rather than counting up the number of times these two values were the same, we count up the square of the difference between our predicted value and the true value. So what this means is if our predicted value is very close to our true value, then this value is going to be small. We square it, and it becomes even smaller. But if this value is large, the predicted value is very far away from our true value. If we square that, that number gets much larger. So we can take the square of the error here and then sum all of that up and divide through by the number of samples to get the average squared error between samples in our data set. So you may see this is somewhat similar to standard deviation, where we're looking at the difference from the mean. That's one way you might do this prediction. But this is the standard sort of, or most common metric, mean squared error. Now that doesn't mean it's the appropriate metric, because in fact there are, as I mentioned, many evaluation metrics, and a lot of them change, or what metrics are appropriate change based on your context. For instance, one of the most common issues you run into is that data sets in machine learning are vastly imbalanced. What this means is you generally have one class that's very common and the other class that's very uncommon. And generally you care way more about the uncommon class and getting those predictions correct than you care about the majority class. So you could think about this as classifying whether somebody has a rare form of cancer. It's very important that you do well in identifying or predicting or classifying samples of tissue into cancer versus non-cancer, but the prevalence of the cancer is very rare. So in this case, accuracy doesn't mean a whole lot here. It's not a super useful metric, because if you're driven just by how many times did you get the label correct, you might reasonably predict the majority label all the time, and your accuracy is going to be quite high. So there are other metrics here called precision, recall, are the two main ones that try and get at, well, of the things that were correct, how many, or of the things that were positive instances, or instances of cancer here, how many of those did you get correct? That's the metric for recall. And precision is of the things that you said were cancer, how many of those actually were cancer? That's the metric for precision. We'll talk about that next in the next couple of lectures. So another thing to mention about how you do evaluation is you should not evaluate your model based on the data you use to train it. So we'll talk about overfitting at the end of this lecture, but this is one of the real problems here. Instead, when we're talking about training, we're fitting our model, determining parameters, you should do this evaluation not on your training data, but on your tested data. You should take a collection of your data and split off some amount of your data that is your test data. And that's how you do this evaluation. You want to evaluate how well your model works on data that's never seen before. So we want to avoid instances of overfitting. We'll talk about what overfitting means in a minute. But this idea that if all we're doing is evaluating on data that we've seen before, data that we've used to train our model, then we maybe just want to predict exactly or memorize our training data, which is generally bad for generalization and seeing new data. And we'll see some examples of that. So instead, we take our full data set and split it into a training set and a test set. Then we take our training data, use that data to fit our machine learning model. We take our machine learning model and calculate evaluations on the test data and use our test data for evaluation. So after we've trained our machine learning model, this thing at the bottom left, we apply it to our test data, and then we use that application of our model on unseen data to evaluate how well our model works. So you should be splitting your data into training and testing sets. There is some nuance here, because the more data you reserve for training, the less data you have for actually doing testing. Likewise, the more data you hold out for testing, the less data you have to use for training. So there are some ways around this, like cross-validation, which we'll talk about in a couple of lectures. Most oftentimes, though, you see splits like 90-10 splits, where 90% of your data is used for training, 10% is used for testing, or an 80-20 split, 80 is used for testing, 20 is used, or 80% is used for training, 20% is used for testing. You can also see validation data sets. So a thing we haven't talked about is this idea of parameter tuning or hyperparameter tuning. We won't go deeply into that, but if you're doing hyperparameter tuning, you have a middle data set called a validation data set, where you hold out a portion of your training data, a small amount, to evaluate whether your parameters are correct or which parameters are best when you're doing this tuning. So to anchor all of this discussion about regression and classification in our lecture from last time on probability, we can see how Bayes' theorem helps us do classification. So we talked about if we have clustered all of our movies based on user recommendations or user ratings, and we want to evaluate, given the genre sport, which cluster is a particular movie going to go into, we looked at the math about how you actually calculate what the probability of a movie being in a particular cluster, given that its genre is sport. And if we want to evaluate the particular cluster or identify the most probable cluster, we maximize this probability over all of our clusters in our data set. So we look at, for each cluster in our data set, we can calculate these sets of values. We don't actually care about the denominator here. So really, we're only just trying to maximize this numerator instance. What is the probability, what is the most probable cluster given this particular genre? And in fact, this is a very standard classification algorithm. Naive Bayes is used very heavily in spam detection. sklearn has a whole implementation for it of numerous kinds. And you can use that as a standard sort of machine learning model for classification, as long as you have or can generate these straightforward probabilistic metrics of how many times a particular class occurs. The classes that here, the cluster is the thing we're trying to predict, and how many times did a particular feature appear in a particular class. So here the features are genre, but it could be words, it could be different kinds of pixels or objects in an image, etc. But that classification into particular clusters or types of movies is not the only thing you could do. You could similarly try and predict not the cluster or genre-based aspects of a movie, but the gross box office return for that movie. So this is a clearly real valued number, and we are not trying to predict discrete labels, but predict the return for each one of these movies. And this box office return prediction problem is clearly a regression problem. You can do the same kind of thing, try and predict the gross box office returns based on genre, based on actors, based on user ratings for similar kinds of movies. Similar sort of supervised learning setup, where you have some movies, you have some features of those movies, genres, actors, ratings, etc., and you have some outcome variable. Here it would be the gross box office return, and you want to build a regression model to predict that value. You'll see how we might build the linear regression model in the linear models case next time. All right, so now you should have a good sense of the difference between classification and regression. Let's now talk a little bit about how we might do classification in a very straightforward or simple way. So we have a bunch of data in our training set or our sample set. This is our training data here, and we want a simple method to evaluate or classify new data into the label space of our existing data. So what we want to do, one simple way may be, well, using our distance metric from previous module, identify what the closest data point is from our training data to our new data, and then use the label for that closest sample as the label for our new sample. And you might imagine this is a reasonable thing. So you see a new person, you don't know anything about them, but you know who their friends are, and you know lots of things about their friends. So you might provide a label about political ideology for this new person based on the ideology of their closest friend. This is a standard homophily kind of assumption, and this actually works quite well in practice. This is called the nearest neighbor approach. We can see this graphically. So given some data set of blue and red labels, we have some new data point, that's the green point here, and we want to evaluate, well, should this be a blue square or a red triangle? So we can use our distance metrics from module 3 to actually find what the nearest neighbor is, the closest data point to this new unseen data point is. And we see that the closest data point here is red. Maybe we assign it the red label. Now this can be problematic because we can end up in situations where a new data point is equidistant between 2 points. So like here, this green dot will claim is equidistant between this red triangle and this blue square. Now you could just do like arbitrary tie breaking here and say, well, we'll just pick one. But another approach for this is to take a vote among our nearest neighbors. So if we have k equals 1, we might likely be in this position where we are equidistant between 2 elements, but if we say k equals 2 or 3, we're saying to become problematic, we may have to be equidistant between 2 or 3 points. Otherwise, we can just take a vote and things will be all right. And we actually see that we can tune these different values of k, how many neighbors do we care about, do we want to include, to get or to change our accuracy. So here, in this case where we say k equals 3, let's look at the majority label across our 3 nearest neighbors. Then this green data point becomes a red triangle. But if we spread this out and look at the top or the 5 nearest neighbors, then we see we actually switch to a blue square where we have 2 red triangles and 3 blue squares as opposed to 2 red triangles and 1 blue square. And you can tune this as necessary as you try and improve your accuracy or your evaluation metric. We can see actually how this might play out in a 2-dimensional case. As we increase our value of k, the number of nearest neighbors we need, we see some change to how these classifications work. You can infer or interpret this figure as being trying to classify data into orange triangles versus blue squares, and this black line is the boundary between data points that get classified as orange triangles versus blue squares. For here, in this case, k equals 25, we'll take 25 nearest neighbors. And you can see across, as we increase the number of nearest neighbors, this boundary starts to look a little different. On the far left, we see a pretty complex boundary with lots of little points or bays in the boundary, where we see these like outposts of blue invading the orange triangle aspects. And as we increase our k value, it sort of smooths out this boundary. In fact, we call this specifically this threshold between our classes as it is called the decision boundary. And the way we interpret this is all elements on one side of the decision boundary will have the same predicted label, and all elements on the other side of the decision boundary will have the other predicted label, even if those predicted labels are wrong. So here we have this orange triangle that's on the left side of our decision boundary, which would say it's likely to be classified as a blue square here. Or it will be classified as a blue square for this k equals 25 approach. So we would say that's actually an error in our prediction. But this decision boundary is quite a useful term. We've seen this idea of decision boundaries before when we talked about k-means clustering, where we have boundaries between where points are going to be associated with particular clusters. So here, any point in this blue region is going to be classified as the blue cluster, or would be classified as the blue class if this was a k nearest neighbors problem. For this case, when we talk about the k nearest neighbors classifier, what we're seeing with this change in the decision boundary is a function of model complexity. That as we increase the value of k, we're actually decreasing model complexity, and we see the boundary sort of smooths out. There's less opportunity for us to have this complex boundary or these complex holes in the boundaries that we see, like k equals 1 on the left. When we get to k equals 25 on the right, we have a much smoother boundary here. But you don't only have to use KNN for classification. You can also use it for regression. The same kind of thing applies, where we look at a data point and when we see new data points, we use the k nearest neighbors and their values. Maybe we average across our k nearest neighbors to find what the regressed value should be. So here, if we're doing k equals 1, we see points between or spaces between our blue points where our prediction for the regression value drops quickly from one point to the next, and otherwise around or very close to these blue points, we essentially predict the same value as the blue points. And as we increase our k value, we see the line, the curve, become less complex. Similarly to what we saw with the classification case, as we increase the k value, we generally smooth out this curve. So here, this idea of decision boundaries becoming smoother applies in both cases. So the higher your k value, the less complex the model is for KNN, or the less complex at least the decision boundary is. So now you have some idea about how voting works for k nearest neighbors classification and regression. Now we'll talk a little bit about the different kinds of tasks you may have for classification. So when we talk about classification, the most common things you see are classifying data into two sets. This most common types are spam versus not spam, this very binary yes or no kind of case. You might have just a simple, like, is this a strawberry or a banana kind of case where we have just two classes. This binary case is very common. And in fact, many of the extensions on classification algorithms rely on this binary class. So even when you're doing what we'll call multi-class classification in a minute, where you have multiple outcome labels, oftentimes, or for many algorithms, you have what's called a one versus rest classifier, where you build basically a bunch of classifiers that say this is an element of a particular class, or it's not. And if it's not, it can be an element of any other class. And you have a bunch of these yes/no sort of classifiers in your model. But that's not the only task that you might do. So binary classification we've seen, but we've seen non-binary classification as well. So here, this is an easy example of a three-class classification problem. So the spam, not spam example you see a lot is a clear binary classification problem, but other kinds of problems exist. So imagine we want to predict the primary genre of a movie, given whatever set of features we have, actors and ratings, etc. Then clearly there's more than just two classes here. There's hard, action, adventure, and so on. And we can predict or you can classify a movie into any one of these categories. And we make some assumption that we're only focused on the primary genre, that each movie only has one primary genre. Then we have this clear multi-class classification problem. Now, like I said, you can sort of convert binary classification models into multi-class models by building one model that says, is this movie horror or not? That's one model. Then you have a second model that classifies this movie as, is this an action movie or not? Is this a science fiction movie or not? And then you collect the outcomes of all of those different models and take which one is the most probable, or which outcome is has the highest score here, which we'll talk about next week when we talk about model uncertainty. Same kind of evaluation metrics apply. You can still calculate accuracy here, just like you did before with the standard binary classification, though how you do weighting might be different. When we talk about evaluation in a couple lectures, we'll see that. But you may have asked yourself, well, a movie can be in more than one genre, right? So how do we deal with that? So I made the crucial assumption, the crucial constraint before, that we're talking about only the primary genre of a movie. We assume we only care about one genre per movie. But certainly you may have multiple genres per movie. That's definitely possible. You have primary and secondary genres, you have 3 like genre crossovers, all that is reasonable. This is a problem, or this is a type of problem called multi-label classification, where a particular sample can have multiple possible outcomes. Now you can apply KNN kinds of things for this as well. So here, say we're trying to predict movie genre for our green dot. We see it's close to this Thanksgiving movie, it's a horror movie, and close to Evil Dead. But it's also close to Happy Death Day, which is a horror comedy crossover movie, and the movie Cabin in the Woods, again, a horror comedy crossover. So rather than just taking the majority label across our, say, 5 neighbors here, we can say take the top 3 labels, or the top 2 labels, the top 2 most common labels, to get a way to do multi-label classification. And we would say this green movie is maybe both a horror and a comedy movie. Now, some of the places that I've done this is I have a program on crisis informatics where we try and predict the kinds of information in social media posts, whether that social media post contains a location, a reference to a location, contains references to damage to infrastructure, whether it contains information about casualties, and a particular tweet can have multiple pieces of information, multiple types of information associated with it. So this sort of multi-label classification problem is not uncommon. All right, so the next thing we'll talk about is overfitting. One of the core aspects in dealing with machine learning is controlling for whether you're over or underfitting your model. So here, suppose we have a set of observations for a curve that we built using a sine wave. So we know what the underlying data is, but we're going to try and build models to predict what this metric looks like. So we have our training data, these orange dots, and we have these test data, these other samples we've taken that we've separated into our testing set, these green triangles. And you see they're all across this sine wave. And we can fit this model with a k-nearest neighbors regression, and remember that the lower our k value, the more complex the decision boundary. And you might think that lower k values and higher complexity is a little bit unintuitive, but remember, in the context of KNN, what we're doing is maintaining individual parameters for every single data point in our data set. So our decision boundary is parameterized by every single data point. Whereas if we're doing KNN with, say, 20 points, then our decision boundary is parameterized by 20 points around the boundary, or the averages of 20 points throughout the data. So we have fewer degrees of freedom there. So our decision boundary becomes more simplistic as we increase k. So here, if we have the most simplistic model, where we take our k as every data point in our training data, then we end up with this straight line. Essentially, we've averaged across all of our data set, and we always predict this same value. So this model is clearly what's called underfit. We're not capturing patterns in the training data. We've got some amount of information here. There is some way that the data has contributed to this prediction, but generally, this is a very simplistic model. It doesn't capture much in the way of patterns, but if data is really imbalanced, like I mentioned in the rare cancer case, maybe the average prediction of people not having cancer does produce decent performance metrics, but maybe is not super interesting for what we want to do. So we can increase model complexity. So say we move from k equals n to k equals n over 2. We get a more complex model. Now we're averaging across the 2 sets of the data, and we get this clear decision boundary around the middle of our data set, where before that we're around minus 0.75, and on the other side of this decision boundary we're about 0.5. We've got some more pattern from the data here, but it's still too simple. And as we lower our k value, we start to capture more trends in the data, which is what we want. We want to be in this case where we are ignoring the little variations that come with error-laden observation, but we are still capturing the general trend. So that's the goal here. But we can go too far this way and overfit the model, where a model is capturing both the general pattern and the noise about individual data points. So here, if we're doing like k equals 1, we're seeing not a very nicely curved line here. In fact, we're seeing like clear perturbations as for each data point. So then we're not necessarily generalizing well when we see new data. So what we call this is overfit. And in fact, there's a balance here between the underfit and overfit of the model as model complexity increases. So for super simplistic models, so always predicting the average value or the majority class, we get large error, both in the training data and in the test data. But we maybe are doing things fast because we have a very simple model. But as we increase model complexity, we hit some sweet spot where our generalization error, our error has sort of bottomed out. But then as we increase our complexity, we start to see larger error in our test data. So again, the training error goes down because as we increase the complexity of our model, we're getting closer to memorizing the full training data. But our ability to generalize also suffers. In the language of learning theory, what we're talking about are the different ways, the different contributors to the overall generalization error. That when we're looking at this graph about the relationship between model complexity on the x-axis and the error that we incur on the y-axis. When the model is not complex, when it's pretty simplistic, then most of our error comes from bias, that our understanding of the model or our ability to model the underlying phenomenon is not captured well in the model that we've chosen. But as we increase the model complexity, our error from bias decreases, and our error from variations, small perturbations in the data, increase as we start to memorize or move into this regime where we're memorizing the underlying data rather than learning the general phenomenon. And the generalization error is the combination of these two things. And the sweet spot in model complexity is where this generalization error is minimized. So on the left side of this graph, we generally refer to this as underfitting. On the right side of this graph, we generally refer to this as overfitting. So as I mentioned, the generalization error is this combination of terms. We have the empirical error. This is the thing that we can observe from our testing data, and we have some other sorts of error as well. So remember, from the perspective of machine learning, we care very much about minimizing generalization error. We can evaluate our empirical error by looking at how well our model is performing on our data, but it's much more difficult to evaluate how much error is associated with the overfit of our model. We don't really know what this looks like because in the general case, we don't have all the data that we might need or might want. We don't have observations across the entire space. So it's not clear where we move from the threshold of memorization or of actual learning trends, learning the underlying phenomenon, to memorizing the underlying data set. So as I mentioned, we want to look for sort of the sweet spot here in model complexity. So how do we reduce this overfitting? How do we try and maintain reasonable complexity? Well, one way is to, rather than reducing complexity, we add more training examples. So we get more data into our system. We can reduce the complexity of our models by applying some constraint. It's called regularization. So we'll talk about regularization next time, but the idea is we somehow include in the math some term that penalizes or reduces the scoring metric for models that are overly complex when we're trying to fit them. So we'll see what that looks like next time. But for now, these are the 4 things we've talked about. You should now have a sense of what's different between classification and regression and supervised learning, how voting works for K and N, the different kinds of classification tasks for binary multiclass, and how multi-label is separate from multi-class, and then what the general idea is behind overfitting, why we want to avoid overfitting, and how it might impact the generalizability of our models. All right, if you have any questions, as always, feel free to post online or come by office hours.